Are we all clear with the forward selection? Okay, perfect, perfect. Now let's talk about bidirectional elimination, right? This is another important method. So guys, what we are doing in the bidirectional elimination, we again selecting the significance level to be, let's say, will enter and will stay at this particular, you can say, all the time we are just plugging in or just making the selection to be like somewhere around 0.05, which is 5% confidence level or the level of significance. Now see, these are very important steps. Bidirectional, as this diagram is giving you an idea, we are going in this way, backward and forward. Now see, this is very important to understand. This is a little complex, but please pay attention. So we perform the next step of the forward selection. New variable must have SL enter to enter. Like let's say we have taken like a particular confidence level to be lesser than 0.05, right? This we have taken the P level, the level of significance, and we have included a variable whose level of significance value is less than 0.05. So we will take that value, we'll take that variable and we'll forward to the next variable. Perform all the step of the backward elimination. So after doing this, we perform all these steps. In the step 3, we perform all these steps of the backward elimination. So these are some of the steps of the backward elimination. We fit the model with all the possible predictors. We consider the predictor if it is less than, you can say, the significance level. If it is less than that, 0.05, we remove that predictor. And if the overall level of significance, if it is less than 0.05, we fit the model and the model is treated. I'll just show you an example like what this bidirectional elimination is trying to say. Let's say for an instance, let me like increase the size a bit. Okay, fine. Now let's say my little bit more. Let's say my p value is lying. I think there is some issue with pen. Just a minute. Okay, let's say my p value is 0.05, right? Let's say for an example, if my p value which I have entered, it is 0.05. Let's say there are some variables which are involved, x1, x2, x3, x4 and x5. Let's say for an example, okay, let me take this color. The p value for x1 is something like 0.001, 0.002, 0.003, 0.007, and let's say 0.07. So this is clear that this particular variable is significance level, it is more than 0.05. So let's say I have taken, see, the first step is saying that perform the next step of the forward selection by taking. So what we have to do, we have to start picking any random variable whose p value is less than 0.05. Let's say I've chosen this variable, right? Let's say after choosing this variable, I have taken a variable which is this. Are you getting my point, guys? So after choosing x2, I have taken x5 because it is a step of a forward selection. Now, while including x5, what it will do, it will make my entire model to be more than 0.05. Isn't it? Yes or no? So what it will say that like what I have to do, I have to eliminate this particular variable, right? After eliminating this, so it's a kind of a elimination. So we have taken a variable, then we have eliminated that particular variable. So choosing a variable is a forward selection, eliminating a variable is a backward elimination. I hope this makes sense. Why they are saying in this way? So after like omitting this, I'll be taking any other random variable, just like a forward selection. Then I'll again check whether my p level is more than 0.05 or not. If it is more than, if it is less than 0.05, then I'll, after choosing this, then I'll again take the another variable. Then again I'll check. If it is again less than 0.05, then I'll keep all these three variables. Then I'll include the other one. I hope this is clear to everyone, guys. I hope this is clear to everyone. Perfect, guys. So this is how bidirectional elimination is working, right? So no new variables can enter and no new variables can exit, right? So your model is ready. Okay, now I hope this is clear to all of you. Now this is another thing which is called as all possible method. So we select a criteria of the goodness of fit. So basically again the criteria is nothing but my level of significance. It is also termed as Akaike criteria, right? There is a documentation which is related to this. So I'll just share you the link on the group itself. What is my Akaike criteria and what is the criteria for goodness of fit? I hope this is making sense. This is the last step, the last method of building the model. Okay, so we construct all the possible regression model. Okay, guys, can you tell me like let's say I got one dependent variable and 10 independent variable. Let's say I got one dependent variable and 10 independent variable, right? So the number of total different kind of model that could be created out of having a 10 independent variable will be something like 2 raised to the power 10. So can you tell me the value? What is a value for 2 raised to the power 10? What is the value for perfect Amolya 1024? So 1024 minus 1 comprises of 1023. So these many cases of models will be generated, and out of this 1023 cases there is only one model which you have to take, right? There is only one model you have to take. Now I do not I do not think that this is making sense. I hope all of you are getting my point. So 10 column means 1023 model. So this is like a lot of combination. So a very small feature, small CSV file will have 10 features, but you in real time you may find sometimes in a particular case that you will encounter more than 10 features. Let's say 100. So 100 column means somewhere around 2 to the power 100 minus 1 combinations. So this is really impossible if you got a high dimensional data which comprises of so many columns. It's not preferred to follow this method because there is only a one unique model which will be selecting the criteria. So what this particular step it is saying that it should you should take a criteria based on a Akaike criteria. So I'll share you the documentation. So after doing that, you construct all the possible regression models. So we have seen that 10 column is making 1023 models, and out of this 1023, you will only select the one with the best criteria. So it's like doing out 1023 different combinations. So that particular one model is the fittest model, right? The feasible model. So this method in general is not preferred at all, although it is one of the methods which we generally take. Can you tell me like when this particular method plays a very vital role? It's for the 10 columns, right? Guys, can you please tell me like when this method is going to like give you, can you please tell me guys? Guys, are you getting like what I'm trying to say? Please reply it on the chat box. Guys, am I audible to all of you? Guys, am I audible to all of you? Guys, I'm not getting any response. Am I audible to all of you guys? Okay, perfect, 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 perfect. Okay, you have to be attentive in like, okay, so guys, what I wanted to say, like, let's say you got 3 columns. So 2 raised to the power 3 minus 1. So total of 7 cases. So whenever you have a low dimensional data, whenever you have a low dimensional data, low dimensional data, then this particular model plays a very vital role, right? So if you got a high dimensional data comprises of 10 features or 100 features, then you do not take all possible models into account. So the most preferred model is the backward elimination. It is highly preferred. I hope are we all clear with the model selection, how to build a model? Perfect guys, perfect, perfect. So I'll just go to the Google Colab again. I think we did this particular file, 50 startup data we did in the previous session. I hope all of you remember the data. Now guys, what I'll do, I'll just, we did some maths. So these are the some of the things that we did. We are left with this training the multiple linear regression model and predicting the test set result. So as you can see, no numbers is there because of the due to the runtime. So I'll just again run all the cells which we have done in the previous session. So our model have comprises of encoding the categorical data. So we also perform the encoding of the categorical data. So you can see there was the predict, the independent variable have been encoded differently. We also do the steps involved in the data pre-processing part, which is splitting the data into the training set and the test set. And we have also seen that test set. So over here, how many fields were there? There were 50 fields, 50 rows. So like 20% test data will be 10 fields going to the test data and 40 fields going to the training data. I hope this makes sense. Guys, I hope this is making sense. Okay, perfect. Now let us do the remaining part. So only 2 parts are left. So guys, similarly what we did with the simple linear regression, the multiple linear regression will also work in the same way. So from sklearn, scikit-learn is a very powerful library because it has all the modules already inbuilt in it. So sklearn dot linear. Why it's a linear? Because linear model will take both the models, simple linear regression as well as multiple regression. So we will be importing the linear regression. See, the Colab is already predicting the code. So let me give this name, the variable as regressor. Let's say it is equal to linear regression. And let's say this linear regression means that, okay, let me write the regressor first. Okay, so what does that mean? That after importing the module from the scikit-learn, the linear model, I am importing one functionality which is a linear regression, and I am giving this linear regression name as regressor. So this is what I'm doing in the second line of code. So this particular linear regressor, what it will do, it will take some more functionality of, let's say, fit. So we have already done all the possible computations in the data, as you can see, encoding the data and as well as importing the data set. So guys, what we will be doing in this, we will be doing the computation on the training data, since training the multiple linear regression on the training set. Okay, so let us see. So we will be including two arguments, xtrain and ytrain. So what this particular output is saying that it has already included the you can say the independent variable. The intercept is fit. So what do I mean by an intercept? The regressor line. So it does not have any missing values, and it was it is not there is a no need to normalize it because the data was already normalized. So this is already checked, right? I hope this is clear to everyone. Please ask with the output. Guys, please ask, right? The output is clear to everyone. Okay, perfect, Vaishnavi. What about others, guys? Okay, perfect, guys. So this is one of the output that I'm getting out of the multiple linear regression model on the training data. Let me predict the test set results. See, we have done the training on the training set or the calculation, or we have applied a multiple linear regression model calculation on the training set. That is what we have done over here. Now let us do the predicting the test set result. So what I'll be doing y underscore pred. So since we are just predicting the values in the test data, and for doing the calculation we are doing on the training data, so we'll be using regressor dot predict. So we'll be predicting by x test. Okay, so it has already have this argument, and let's say the precision. Okay, so this is one more term. I'll be just letting you know what is termed as precision. Don't be get scared with the code. So as you can see, already it is populating. So set underscore print option. Let's say precision. So this is already giving you the argument. So what this is highlighting that, okay, I'll just have a quick walkthrough. So guys, precision, these options determine the way floating point numbers, arrays and other NumPy objects are displayed. So this is actually will determine how the number should be displayed in the output. So number of digits of precision for floating point output may be none if float mode is fixed, or to print as many digits necessary to uniquely specify the value. I hope you remember, like it's similarly like calling out the digits in the output to a specific decimal places. I hope this makes sense. I hope all of you have heard this term which is called as float. Have you heard this term which is called as float? Perfect, guys. So floating is something related with the values which is lying after the decimal places, floating point numbers. So I'm just taking the floating point number to be till two decimal places in the output. Now, see, I'll be utilizing some more arguments. Like I want to see NP. I'm just taking from the NumPy library NP. That's why we have called initially NumPy as NP. I think this we have already discussed in the previous classes. NumPy is NP. So NP dot concatenate. Concatenate is generally used to combine. So print the value. So basically, this concatenate function will combine the result. So what kind of result I want? I want ypred, this particular part in the testing data dot reshape, and I'll be just explaining the code. Let me write it. Length of ypred comma y underscore test dot reshape. Now again length of y underscore test comma 1. Okay, let me just cross check everything is fine. Okay, let me execute the code. Okay, there is some error. I think there is some error which is related with the writing. Okay, let me cross check. Okay, this is fine. Okay, I think the brackets error. Okay, see guys, you can see while just toggling over the brackets. So I think I have just done something which is related to the brackets. I'll just cross check. There should be two brackets. And like it happens sometimes, like you encounter these kind of issues in coding. Okay, okay, the code is fine till here. Okay, I haven't included the argument over here. Similarly, like this way, right? Okay, I think I'm getting that. So, okay. Okay, guys, I think I am facing some issue with the brackets part. Again, the bracket part I'm including. Just give me a sec. Test dot reshape is fine. Length y underscore test comma 1 should have two brackets. Okay, this bracket is not being represented. See guys, this issue comes once you write the coding. So again, a bracket involved. Can you figure out, guys, what issue is persisting? Perfect. I hope it is totally based on the element calling, right? So these are my predicted values, right? Which is based on the output. Guys, I hope all of you are getting it. What was the issue? Actually, the thing was this particular thing is important. See, due to the precision, the float value does not created after the 2 decimal point, right? All of you are getting it, guys. What I'm trying to say. That's why, due to the precision, the float value is not getting created after the 2 decimal points. I hope this is clear, right? Due to this precision, so we have used the yprint with the help of the test data, right? Now in the output, what we are see this argument is printing this one, the test data. So both of the argument have been printed from the test data. See, we have printed 2 arguments. One is this argument, and one is this argument. Now this is the actual test result which we have predicted. This was the actual data, right? And this is a predicted data. I hope this is clear to everyone. As you can see, the first argument is from the yprint. Guys, all of you can see this. The first argument is from the yprint, and the second argument is from the ytest. So ytest is my actual data, whereas yprint is my predicted data. So actual data is this, predicted is this, actual is this, predicted is this. And we can see that for most of the values, my predicted data is almost closer to the actual data, isn't it? So our you can say the multiple linear regression models works almost efficiently, right? I hope this is clear to everyone. Guys, I hope this is clear to everyone. Please ask anything if you have any doubt. I'll just call it a day for today. All clear, guys? Clear to everyone? Vaishnavi, this can be done with the help of scattered plot as well, but for that I'll be creating so many scattered plot. It's just like I'll just show you on like OneNote, something like this. So many scattered plot will be created. So like while doing the visualization part in the later classes we'll be also be doing, but over here we are just more or less focused on the values, right? How the model is how the model is doing the prediction with the help of the regressor line. So this is a prediction of a regressor line, and this is a actual data. So we can see the differences. I hope this is clear. Yes, perfect, perfect. Yes, Vaishnavi. Visualization will work in the later classes. We will be working on, there is a lot of thing which is based on the visualization. But as of now, this is something which is related to multiple linear regression. And this is, you can say the steps one should follow. I'll be just sharing you the template, right? Okay. So guys, let's call it a day. Mm, so keep on learning. I'll just share you the code right away. And the data I've already shared in the previous class. And if you want to refer to any of the missing part, you please refer to the video which is already been shared to you, right? Okay. Thank you guys.